today. Okay, inverse. You know the word inverse from inverse operations, right? Okay. What's an inverse operation? Anybody remember? Kind of like the opposite. So adding undoes subtracting, multiplying undoes dividing. So we have that word that you're familiar with, but we need to apply it in a new context for inverse relations. And inverse relations are found by switching the x and the y value. So if we have this relation, if you remember, a relation is just a set of ordered pairs that may or may not be a function, but it's a set of ordered pairs. So in order to get the inverse of this relation, all you do is switch the x values and the y values. So if we switch these, that means x becomes what? X is 2, x becomes 5, and y becomes 2. On this one, x becomes -4, and y becomes 3. So for an inverse relation, all you do is you switch the x and y values. So if you could write that down so that you are seeing what's happening here. And we also know that relations can be written down as graphs. So the reason that you all have graph paper in front of you is that you're going to graph the relation, and then you're going to graph the inverse of the relation. But what I'd like you to do is I'd like you to either do it with a pencil for one and a pen for the other, or maybe you can do X's and dots, or maybe you can use one color and another color, or a highlighter or something, so that you're differentiating between the relation and the inverse. But I would like you to make a graph, please, of both. And I'll put this on pause for a second so that you have time to do that, and the people who are listening at home would have a chance to. And now that you've got the graph done, what is it that anybody notices? Does anybody notice anything about the original graph points and the inverse graph points? Does anybody see anything that stands out? What do you see, Dylan?
It's like, okay, so if you look on the top, near the Y, there's like 3 black ones and then 1 white. And then on the opposite side, there's 3 red and then 1 black. So it's like the same but opposite.
Okay, so it's like the same but opposite is what he said. That I like the way that you explained that. You explained it very well. So what he noticed is that the pattern is the same, but it's on the other side. Okay, we say that it has symmetry. Okay, and yes.
That's what I was gonna say. I was gonna say, like, if you go, like, if you were to flip the graph like this to where you know how there's 4
here,
right
right down the middle.
You know,
Aha.
that's the axis of symmetry. That's what I was trying to say.
Excellent. Okay, so if you draw the line diagonally, that is the axis of symmetry. I love those good math words. So it's the axis of symmetry. The axis of symmetry is that diagonal line through, right through there. So you can use your ruler to go ahead and draw that in. And I made it dotted because it's not actually part of the graph, but it's an important fact that when you look at a relation and its inverse, that you do have an axis of symmetry that goes along that line, and it's the x equals y line, because 1, 1, and 2, 2, and 3, 3, those are the ordered pairs along it, where x equals y. This is our graph. Even if you thought about it as y equals mx plus b, y equals 1x plus 0, up 1 over 1, all the different ways you can think about a graph. There's our axis of symmetry that goes right along there. So if you folded it right along there, thank you for noticing that all. I know that it was good that you noticed it before I actually said it. But that's our relationship between the relation and its inverse, just switching the x and y's back and forth like that. So you can do that with a set of ordered pairs that are listed like this. But what we can also do is we can run that process when you're given a relation, you're given a function. You can find its inverse, and the inverse will be a relation, but that inverse may not necessarily be a function. So we'll take a look at an example. I don't have a whole ton of examples for you today, but just enough for you to understand what's happening and then be able to practice with your homework. And please make sure that when you do your homework that you're really practicing so that when you get to the test or quiz, you're not just trying to remember something you saw once. You need to do the problem so that you can have it ingrained in your brain and then know what you're doing. So to find the inverse, I'll get your question in a minute. What you need to do is you need to switch the x and y even in the original function notation. Switch the x and the y and then solve for y. Now, what was your question? All right, so when I say switch the x and y, I mean literally take the x out and put the y there, take the y out, put the x there, and then work to get y by itself. Yes. It is, yes, it's currently happening. So here we go. We switch our x and y, and then we want to solve for y, and that'll give us our inverse. Even if the original didn't say y equals, if the original had said f of x equals x squared minus 1, that f of x would be your y, but then you'd switch it out and put an x in and then solve. Yes? We're trying to find the inverse. Now, the ordered pairs are nice when they're in a list because you just switch all the x's and y's. But when you have an equation like this, you can switch all the x's and y's, but you're switching the billions of them by just.
And it'll give you.
It'll give you the inverse relation. I'm calling it a relation because even in this case, we're not going to end up with a function for our inverse. We're going to end up with an inverse that when we graph it, you'll see that it does actually work that way. But so we want to get y by itself, so we add 1 to both sides so that you've got x plus 1. And then how do you undo the square? Square root, but there's two answers, right? The square root of y gives you plus or minus x plus 1. So our inverse relation looks like this, the square root of x plus 1. So we can graph this one easily because you're used to graphing parabolas. We know that this is a parabola, the parent function of the parabola, and what does this minus 1 tell you? This one. What does the minus 1 tell you in the original function? The whole thing went down. So we have that. This one, however, because it has plus minus, we'll have to do a little bit of thinking to figure that one out. But what I would like us to do is I would like us to graph the original function. So if you remember, we have this pattern. Here's our graph. So please take your graph paper. The ordered pair 0, when you plug in 0 to the original, you get -1. When you plug in 1, you get 0. When you plug in -1, you get 0. Here's our axis of symmetry. When we plug in 2 to the original, we would get 3. So we've got our original parabola looking like this. Now our inverse relation, there's a couple of ways that you could handle it. You could either plug in values to find the other, or what you can do is you can draw in your diagonal line, draw in your x minus y. So I actually would like you to do it this way so we can apply this idea of our graphing for the inverses. So you're going to put a line in. I'm just going to put in, I can do a dashed line with my tools, so I'll go ahead and do that. But we're going to put in your dashed line, start down here and go up through like this. So please make sure it's like right through those corners, very carefully adjust your ruler. And then what you can do is you can go point for point, bringing over for our inverse relation. So I'm going to use this, make red dots. Okay. Okay, so this one here, you can see that it's like right on the corner here, so I can bring this, you're switching the ordered pairs. The original ordered pair is 2, 3, so the new one is 3, 2, and it just jumps right over the thing. Okay, this one has to jump to this side. This one has to jump over here, but this one jumps over here. Okay, so they switch over the line. This one over here is the one that's furthest away. The original is 1, 2, -2, 1, 2, 3, -2, 3. So if we go to 1, 2, 3, -2, we get down here. And what we find when we try to draw it is that our parabola ends up turning on its side. And it's no longer a parabola well, it's no longer called a parabola anymore. It's the same basic shape. Yours is going to look nicer because it's easier for you to draw like that. But so what happens is we do still have that inverse idea. It switched over. This one, though, is not a function. How do we know that's not a function? Well, because I said it, but do you remember what's our test for functions on a graph? Vertical line test. Thank you. So here, the vertical line test, if you draw a vertical line here, there's many places where it hits more than one spot. So this inverse relation doesn't happen to be a function. If you remove the plus or minus from it, you could have a partial inverse, and then you'd have the square root, and we'll just move along with that. Okay. So not a function, function. If you could make sure to write that into your notes, that would be fantastic. I'll give you a moment to go ahead and finish writing that graph. And taking a look at this one, we want to find the inverse of this. So I want you to take a minute. I want you to switch your x and y's. I want you to do this one. This one should come out to be a little bit simpler, but I do want you to practice. And then I want you to graph the relation. And I want you to graph its inverse. And then answer the question, is the relation a function? And is the inverse a function? So I'll give you a minute to go ahead and work on that, and then we'll talk about it. What's your question?
What music were you listening to?
We'll hold that question because right now we're recording this. And so we are going to just take a look at how this happens, because some of you are there, but some of you are not quite there. When you switch the x and y, you put the x in here, you put the y in here, leave everything else. So don't bring the 2 with it when you switch the x and y. Then solve for y by subtracting 8 from both sides. And then dividing both sides by 2 so that you're getting y by itself. Now, notice that I didn't leave it as a fraction. Technically, it's still correct to say x minus 8 over 2, but it's more convenient for graphing because you know how linear graphs work out. This is an mx plus b equation. So our inverse is y equals 1/2 x minus 4. Or if this one's f of x equals 2x plus 8, this might be g of x equals 1/2 x minus 4 if you had the 2 that you wanted to think of as inverses. And then to graph them, do what you, each one's a line. So the first one, the stretches, compressions, all those are great, but when you just have linear graphs, do what you know as far as mx plus b. This one would start at 8 and go up 2 over 1, rise over run. This one will start where? If you just are graphing the inverse for line. Mx plus b. So we'll start at the -4, and then our slope up 1 over 2. I did put in this this line of symmetry just so you could see it, but here's our graph. Here's our 8 for our original, up 2 over 1, but then you can go the other way, down 2, left 1, down 2, left 1. So you've got that nice slope of 2 for the original graph. Here is our inverse graph. Notice that each one does come right across, but this one's a little harder to do. If you if you're reversing the points with line of symmetry, because you know so well how to make a graph like this, but once you've got it, you can see that it's symmetric, and that's fantastic. And both of these, in this case, are both functions. Vertical line test doesn't hit more than 1. Vertical line test doesn't hit more than 1. So each relation in this case is a function. So sometimes you get functions for both, and sometimes one's a function and the other is not a function. Okay, so that's what we have, and I'll just leave that there, and I'll wrap this up for those that are rewatching it at home. And don't forget to do your homework. I want